Modern transformer models run on continuous floating-point arithmetic. This is a pragmatic compromise, not a mathematically principled design. Because the math is continuous, compressing these models means relying on statistical quantization, rounding numbers, and hoping the errors average out. This continuous space also forces unstructured memory management. When a model's context window fills up, deciding which key and value vectors to evict from the cache becomes a probabilistic guessing game. The Shannon prime architecture abandons this continuous carrier. It replaces floating-point approximations with exact algebraic and topological discrete structures. Anchoring inference in the rigid laws of discrete mathematics provides mathematically proven lossless compression and strict deterministic bounds on memory. First, on the left is continuous matrix space. On the right, Shannon prime shifts the compute substrate to a discrete elliptic curve over a finite field. Second, instead of massive continuous vectors, a KV cache becomes finite labeled trees. These substrates act as drop-in replacements for layer operations and cache updates in existing transformers. By combining these two substrates, the model stops operating as an engine of statistical approximation. It becomes a rigorous, exact, discrete dynamical system. In this architecture, the transformer's residual stream is redefined. Instead of a continuous vector, it acts as a point trajectory navigating an elliptic curve, where each layer applies a discrete endomorphism to move it. Because compute state is bounded by the curve's discrete geometry, the maximum number of distinct reachable states at any given layer is strictly capped. This boundary is defined by the Hasse-Weil theorem. The formula shown here calculates the exact maximum point count for a given curve reduction. This translates to a hard data capacity ceiling of approximately log base 2 of p bits per coordinate, mapping directly to hardware word size. This bound functions as the true Shannon limit of the model. Once the trajectory visits this maximum number of states, adding more parameters or depth cannot extract any additional information from that layer. Standard post-training quantization formats like AWQ or GPTQ require massive empirical calibration datasets to correct for arbitrary rounding errors during compression. This equation perfectly demonstrates Shannon prime's algebraic alternative, the Frobenius endomorphism. On a complex multiplication curve, the Frobenius endomorphism commutes exactly with every single layer endomorphism. This means reducing precision from FP16 down to FP8 is executed purely as an iterated Frobenius application, completely bypassing statistical rounding. Because the operations commute perfectly, the underlying multiplicative relations of the weights are preserved exactly. This structural preservation enables zero calibration compression. Quantization error is mathematically bounded by the curve's properties, rather than estimated through extensive data testing. We can push this precision further using Turing's criterion, which categorizes how different primes behave based on their traces of Frobenius when used as a quantization axis. Under this criterion, inert primes have a trace of exactly 0. Quantizing along an inert prime introduces absolutely 0 systematic drift to the curve. Split primes, on the other hand, carry a non-zero, analytically bounded drift governed by the Sato-Tate measure. This readout shows Shannon prime's asymmetric FP10 format. A 2-bit inert prime channel ensures 0 drift performance, paired with an 8-bit split prime channel. By selecting 41, the smallest split prime, the format guarantees minimum bounded variance on the 8-bit channel, while the 2-bit channel remains perfectly static. Intelligently routing bits through inert and split prime channels allow engineers to deploy variance-free, mixed-precision models entirely devoid of empirical calibration data. Memory compression faces a different challenge. Continuous key vectors in the KV cache carry specific rotational positional structures. Generic flat quantization destroys this positional data. To preserve this structure, the framework uses the Knight Spinner Tree Encoder, or KSTE, mapping the vectors into discrete topologies. The KSTE completely discards scalar numerical values. It extracts only the order invariant signature of the key vector, specifically the rank and sign of its components. This animation shows the output. The encoder maps a dense 128-dimensional continuous vector into a highly structured 60-node, 3-label tree. The 14 anchor lanes form the top-level nodes, while the 60 residual lanes are encoded as depth paths. This 60-node tree is packed into 60 bytes, 15 for labels and 45 for parent pointers, fitting exactly inside the existing 63-byte spinner block format. Because the topological structure is reconstructed on demand from this layout, the system generates this structured memory with zero extra storage overhead. KSTE re-engineers the KV cache. Instead of a bucket of raw floats, memory becomes a discrete, structured hierarchy, setting the stage for exact cache management. These finite labeled trees are governed by the Kruskal-Friedmann well-quasi-ordering theorem. This diagram visualizes homeomorphic tree embedding. It is a strict topological test to determine if a query tree can be structurally folded or injected into an existing key tree. This dictates the sieve eviction policy. If a query tree perfectly embeds, it is guaranteed mathematically redundant. The token is safe to evict. This mechanism includes a strict failsafe based on Harrington's conservation principle. Any failure immediately yields a primitive recursive finite local witness, making every error traceable. Because every single eviction decision is rigorously refutable, the Friedmann sieve upgrades context window management from a probabilistic gamble into a mathematically proven certainty. The Shannon prime framework proves that transformer inference no longer needs to operate as a continuous approximation. It relies on two mathematical structures working in tandem: exact algebraic precision scaling via the Frobenius endomorphism, and exact topological memory bounding through the KSTE and Friedmann sieve. This exact mathematical foundation stands in stark contrast to the industry's reliance on brute force parameter scaling and empirical datasets. The rigid boundaries of algebraic geometry and topology define the final capacity of transformer compute.